Missing data is a pain to deal with, and is all too common a problem when you want to perform analysis on your data and produce amazing insights. You may think that your only option is to sacrifice the missing data to the analysis gods, but there's a really elegant technique to help you infer what the missing values are. That is the technique of interpolation. Hi folks, I'm Trent. I've been a professional data engineer for 5 years, and in this video, I wanted to take you through a somewhat advanced data cleaning technique in Pandas. This is a follow-up to my last video on data cleaning, where I went through the basics of data cleaning in Pandas. I'll leave a link to that if you're interested. I'm going to use a practical example to illustrate filling in missing data using interpolation in Pandas. And at the end of the video, I'll discuss the difference between interpolation and a technique you may be familiar with called regression. Let's get to it. Jumping into my editor over here, I'm going to be using a Jupyter notebook to go through the example. And I've got the packages Pandas, Matplotlib, and NumPy installed. So if you want to follow along or want to reproduce this example, be sure to have those installed. And I've just set a couple of options over here to make things easier to view in this notebook. I'll also leave a link to my GitHub if you want this exact notebook to follow along with the video. Alrighty, so let's run the imports. All right, now that we've got our packages loaded, let's take a look at our data. I've just stored this data in a CSV file called data2becleaned.csv, and I'm going to read that in using the pd.readcsv method over here. All right, let's uncollapse this output and take a look at the data we'll be dealing with. So as you can see, this is a pretty simple data set. We've got a date column and a sales column. I wasn't too creative in terms of what sales this would be, but you could imagine it for any kind of business or any business of your choosing. So for each day, this is daily, we're recording a set number of sales. We can say that it's the number of sales in dollars perhaps, and we can see that this is steadily increasing. But as we scroll down, you can see that some days have missing values over here represented by this nan or not a number value. We keep scrolling, we can see a few more cropping up. If I scroll to the bottom here, there are quite a few in sequence happening over here, just nan values repeating, and then the data picks up again. Let's recollapse this output. So what I'm doing here is I'm just going to take a look at the metadata associated with my data using the df.info method. What this prints out is it shows us our two columns. We can see that we have 50 entries over here. For the date, we have no null values, which is good. Unfortunately, the date is being stored as an object type. We'll need to change that to a date time type just to make it a bit easier to work with. And then we can see we are actually missing 9 values for our sales column over here. And that's being stored as a float type, which is good. All right, so just to make the data easier to work with, what I'm actually going to do is convert our date column really quick. So to do that, I'm going to state df, select the date column, and then use the pd.toDateTime method to convert our date. So to do that, we need to give it our column, so df.date, and a format for our date format. And we can see that our date format is year, month, and day. So let's go ahead and specify that using %y for year, dash %m for month, dash %d for day. Just convert that. You can see the representation of the data hasn't changed, but if we do our df.info again, we can now see that this is a date time 64 type, which is exactly what we want. I've added some code here just to plot out the data so that we can get a better idea of what this looks like and the effect that the missing data has on our data set. So to do that, I have used Matplotlib over here to specify a figure. I've just specified a fig size of 12 by 5, just so that it's big enough for us to see, and then used the .plot method over here. And on the x-axis, specified the date. On the y-axis, specified the sales with a dot marker, given it a label, given it a color of gold, gold for sales, money, guess it kind of works, right? And put a marker on the dots just so that they stand out a bit more on our plot. I've also just added an X label, Y label, and rotated the X values to make it a bit easier to see. All right, let's run this and take a look at our plot. Alrighty, so we can see our time series data over here. We've got our different days and the daily sales. You can see we start off at about 0 over here and steadily increase, but we can see some gaps appearing like over here, probably over here, and a large gap over here for these dates. To make things a bit easier to see, I'm going to add some dashed lines or some vertical lines where we have missing data, just so that it's obvious where we are missing data. Of course, it's obvious over here, but there are some values in between that aren't so clear to see. So let's add some code for that. So we want to get the dates for which we have missing values. To find that, I'm going to specify a new variable called NA_dates for null dates. And let's set that equal to df and filter our data frame at df sales dot is NA to specify we want where the sales column is null or is NA. And to select the date column, I'm going to just specify date over here. And all we want are the values out of this. So I'm going to use dot values to extract the date values for which we have null values. Let's print those out, NA dates. And we can see this gives us a printout of each date for which we have missing values. All right, so we want to plot each of these missing values. I'm just going to modify our plotting code over here. Let's add a couple lines and let's loop through each date value or date value in NA dates over here. So for each value, what I want to do is plt dot ax vline. So for axis vertical line, right? I want to plot the date value. And let's make the line style equal to dashed. So we've got a dashed line, and we'll make the color equal to black. So a black dashed line for each of the NA dates that we have. We want that to appear on our plot. So let's run this, and we can see we get our dashed lines wherever we have missing values. This just makes it a lot more clear to see where we are missing data. We can see we're missing one over here, one over here, one over here, and then a whole bunch over here between these two dates. So now we come to the question of how do we go about filling these different missing dates? I mean, we could just drop this data, but we're losing a whole bunch of sales information if we do that. So to fill in the missing values, one option might be to take a look at these values over here, the values surrounding one of our missing values. Let's actually zoom into that. Looking at the 2 points that we know, we can see that our missing value in between is halfway between the two known points, right? So an intuitive way to fill this in might be to say, let's just take the halfway on the y-axis, the halfway point between these two known points, and use that to fill our missing data. And that is exactly what interpolation or linear interpolation, the simplest form of interpolation, will do. It will draw a straight line between these two known points and then use the contact between that straight line, so where this dashed line appears, to fill the missing value. For this patch where we have multiple missing values, we can do something similar. We have two known points surrounding these missing values, and if we drew a straight line between these two known points, wherever that straight line intersects this missing value line over here, we could just use that value to infer what it should be. Again, this is exactly what linear interpolation is. To be a bit more rigorous, let me introduce some of the theory around linear interpolation to make it a bit more clear. All right, so given 2 points, x1 and y1, as well as x2 and y2, so much like we have over here in our example, 2 known data points, we can find a point y star for a given x star, so that's our missing data over here, using linear interpolation. What we're assuming, and this is the big assumption behind interpolation, is that our data follows a pattern like y equals some coefficient, a, 0, plus another coefficient, a1, times x. So the typical kind of linear equation over here. And what we're going to do is solve for these two coefficients, a0 and a1, using our 2 known points. So solving for those 2 points, substituting in x1, x2, y1, and y2, we end up with coefficient equations that look like this. A1, which is the gradient of our straight line, and A0, which is the intercept of our straight line. We can then find our missing point, y star, given an x star, so our known date in our example, our sales date, between x1 and x2, so we're assuming that it's between the two, and that is true over here, right? We've got our point that is in between our two known x points and substituting that into our equation. So we find y star by substituting in our known data points and get the resulting y star value. So that is the kind of technical side of it, but Pandas makes this super easy. We don't actually need to know all of this, but I think it's nice to know some of the theory before just applying some random technique, right? But in Pandas, we don't have to know about all this. Everything happens under the hood for us, and I'll show you how to do that right now. Okay, so let's add a code block, and to interpolate our data or interpolate our sales data, what I'm going to do is specify our df and create a new column. Let's call it linear interp for linear interpolation. Over here is equal to df, select the sales column, and then simply specify dot interpolate over here. So using this interpolate method. And within interpolate, we need to specify a keyword method, and we can just say linear over here. So linear interpolation is exactly what we want to do on top of this data and produce a result. Let's actually print out the data frame just to see the results side by side. So running this, you can see we've got our new column, linear interp for linear interpolation. And if we scroll down to find a missing value, so over here on like the 16th of January, we have a missing value. We can see that the interpolated value has appeared. And this is exactly the midpoint between the two known points, the straight line kind of midpoint between these two known points of 13.18 and 15.22. We get the result 14.20. Alrighty, so let's see what this looks like if we plot it on our plot over here. So I'm just going to add a line. This extra line of code that I've added over here will simply plot our linear interpolated values as a line with a label stating that it's the linear interpolation over here. So I've just added this label for clarity, and I've plotted it in red. So let's go ahead and replot. Plotting out our interpolated values on top of our known data, we can see a straight line appearing between our known values and the missing values. This point of intersection is exactly the value that we would assign to the missing values. To make things look a little better, I want to change the order of how I'm plotting these just to make it easier to read. So I will overlay the interpolated values with the sales data instead. Let's just rerun that. Yeah, and that looks a little nicer. So this just shows the linear interpolated values that we get that fill in our missing values. Now, a straight line is great to predict our missing values, but you may be thinking, what if my data shape is more complex? Or I assume that my data shape is a little more complex than just a simple straight line. Well, we can extend this idea of linear interpolation into polynomial interpolation, which instead of using a linear function, will use a quadratic or cubic function to model the data in between our known points. Let me show you this for a quadratic function or a polynomial of order 2. So for a slightly more complex model for our data or complex equation to fill in our missing data, we can use a quadratic equation, which is simply an equation of the form y equals a0, so some intercept coefficient, plus a1 times x, so up to here, this is much like our linear assumption, but then we can add another term to this equation of a2, so yet another coefficient times x squared, which would allow us to assume that our data is a bit more bendy in between, right? Like there's more of a curve-like shape to it, and probably a better approximation for more complex data. So similar to linear interpolation, the idea is to use data points, known data points, but in this case, we need 3 data points. Why? Is because we have 3 unknowns in our equation over here, these 3 coefficients. So we need to have at least 3 known data points where our missing value appears in between those 3 data points. So solving this equation using our known data points will result in coefficients of this form over here. And as you can see, just adding that single term has made it a lot more complex, right? And we can do this arbitrarily. By that, I mean we can keep adding more and more terms to our interpolating function over here to make it as complex as we need. Now, as I said, just adding a single term has made our equations more complicated. You can imagine what happens is if we made our equation an order 10 or order 15 type function, these are going to get harder and harder to compute. Now, in the real world, typically we would go up to order 3. That strikes a good balance between complexity and accuracy. But just to illustrate the point, I'm going to stick with quadratic for now and show you what that looks like. So again, Pandas makes this really easy to do, but it's nice to know some of the technical details. So let's go back to our interpolation using Pandas. Scrolling back up to where we did our linear interpolation, we can now do something similar and instead specify something like a column called quadratic underscore interp for interpolation is equal to df sales dot interpolate again, but this time we can specify the method equal to quadratic. So this specifies two pandas that we want to use a quadratic equation to interpolate our data, and it will go ahead and apply that to our data set. So let's run this again, and expanding the outputs, we can see we now have a quadratic interpolated function, and for our known data points, exactly the same, right? We're not interpolating these points because they are known. If I scroll down though to where we had a null value or missing value, we can see that we get two different results, 14.2 for linear and about 14.34 for the quadratic interpolation. So slightly different. Let's take a look at what this looks like on a plot. So I've just copied and pasted the plotting code from above over here, much like we did with the linear interpolation, but just specified that I want to plot out the quadratic interpolation with a label of quadratic and a color of blue. So let's rerun our plotting code and see what we get. So we can see that we now have this blue line on top of our red line, which was our linear interpolation. And if we zoom in, let's actually zoom into this guy. If we zoom in, we can see that for this first missing point, there isn't much difference between the blue and red lines. So the quadratic and linear interpolation is quite similar. Where we can start seeing differences, more pronounced differences, is where we have multiple missing values. This is because the quadratic interpolating function is using this point, and then suddenly this point over here, and fitting a quadratic function to those 3 points. And you can see this deviates quite a bit from our linear function over here. So instead of these intersection points between the red line and the black dashed lines, the quadratic interpolator is using the intersection between the blue line and these black dashed lines over here. Now, as I mentioned, we can make our interpolating function as complex as we need or as we want. We could keep adding terms of higher and higher order and keep getting bendier and bendier curves to predict the missing data in between our data points. We're only limited by how many known points we have, because as we noted, for the linear function, we needed 2 points. For the quadratic function, we needed 3 points. For a cubic function, we would need 4 points, right? So we're limited by how much data we actually have. That is the upper limit to what we can do. To really flesh out the discussion on interpolation, I wouldn't be doing a service if I didn't mention the most powerful form of interpolation, or generally the most powerful form of interpolation, which is called spline interpolation. It's a pretty funny name, actually, now that I think about it, a spline. But to describe what a spline function is, I will resort to using a technical definition. So let me go and grab that. I've brought up the technicals around a spline interpolation, and I'm going to treat this at quite a high level. But if you do want to go into the detail, I'll drop a link to a MIT article or MIT book chapter that I used as reference for this video. If you really want to get into the technical details, I'm just going to go through this at a high level. The most powerful or most robust form of interpolation is actually a cubic spline. So we're going to use multiple cubic polynomials to interpolate the data. Just to touch on the technical definition of a spline interpolation, just to give you an idea of what the difference is between a spline interpolation and a polynomial interpolation. A spline will effectively cut up the domain, or kind of the x-axis in our case, into pieces, or treat it as different subsections. And instead of using a single polynomial function to interpolate our data, it will use multiple polynomial functions to interpolate our data. In the case of cubic spline, it will use multiple cubic polynomials to interpolate our data and make sure that they fit smoothly together. So this section over here, talking about the different rules that a spline interpolant or spline interpolation function has to obey, all this guarantees is that the different interpolating functions fit together smoothly. It's a little technical, but all you need to know is that polynomial interpolation, one function; spline interpolation uses many functions that connect together in a smooth way over different sections of our x-axis. Again, I'll leave a link to a more in-depth discussion of interpolation. I'll also leave the link to this notebook, of course, if you do want to go through this in a bit more detail. And again, Pandas makes this way easier than understanding all of the math behind the spline interpolant. All we have to do is change our keywords. So let's scroll up to our interpolation again. To do this, I'm literally going to copy this guy, but instead I'm going to say cubic, let's say cubic spline interp. Yeah, and the method I want to use is, let's just grab the IntelliSense, so cubic spline, there we go. So we just need to change a keyword, and that's all we need to care about, and use the technique of cubic spline interpolation. So rerunning this, again, we now have a third column where we've done interpolation. And just to scroll down to our example value once more, we can see our linear interpolated value for this missing value over here, the quadratic interpolation, and finally the spline interpolation over here. And again, let's get a visual representation of what this looks like. I've just added a line over here, another plot line to our plot code to represent our spline interpolated values, and made the color green. So let's rerun this and see what we get. And we can see that our spline interpolation is pretty similar to our quadratic interpolation. Slight differences. Let's zoom into this a little bit. But you can see that the spline interpolant deviates slightly, but gives a more smoother feel to the interpolated values over here. Now that we've interpolated our data using 3 different methods, the question becomes, which method is best for our data? Now, there is a mathematically rigorous way to show that spline interpolation minimizes the error that it incurs when we interpolate with it. But for our specific data, we can do a more practical experiment to check what error we've introduced via interpolating our data. To do that, let's start a new section of the notebook. To estimate the error that we're introducing with each of the different methods, what I'm going to do is create a new data frame called errors df as a copy of our original data. So let's take df and specify date and sales over here. Make that a copy of our data. Let's just print that out to make sure we're getting what we expect. So yep, this is just a copy of our original data with all the missing values. Then what I'm going to do is purposefully introduce some missing values in a new column called dummy sales. So I'm going to purposefully exclude some of the known data so that we can interpolate on it and then see what the difference is between the real value and the interpolated value. So to do that, let's first create our dummy column. So errors df dummy sales is equal to errors df sales. So we'll start off with our original one. So errors df sales, rerun that. We've got a new column called dummy sales. But now what I'm going to do is purposefully exclude some of the sales data. So let's do errors df. This time I'm going to use the keyword .log to specify or filter my data on specific values. So to make this a bit more clear, what I can do is something like errors df .index as my row indexer, right? And say that the index value mod, let's say every 5th value. So this operator is just the modular division operator. So basically it will give us a result if the value is divisible by 5, it gives us a result of 0. And if it is not divisible by 5, it will give us a result that is non-zero. So I'm going to say for every 5th value, so when the mod is equal to 0, every fifth value of the index, I want to set my dummy sales. So I'm going to specify my column here. So dummy sales over here. So I've got a row indexer and a column indexer. I'm going to make that a null value. All right, so let's take a look at what that gives us. So we can see now that every fifth value, so from 0 over here, is set to nan, or a null value. So every time I hit an index that is divisible by 5, I now get a null value. So 5, 10, 15, etc. To make this a bit more rigorous, I actually don't want my index to start at 0. This 0th value is going to be tricky to interpolate because there is no data prior to it to do an interpolation. So to correct for that, all I'm going to do is actually say not just index, but index plus 1. And this gives us a result that we're looking for, right? Every fifth value is now set to null. All right, let's collapse this result, add a new code block. And now what I'm going to do is interpolate on top of our dummy sales data using the different methods that we discussed. The code that I've added here is simply the interpolation of the dummy sales column this time. So not just sales, but our dummy sales, where we've purposefully excluded data using each of the different methods that we discussed. So linear, quadratic, and spline, or cubic spline to be more specific. Let's run that and see the result we get. And now we can see that we have our extra columns. And if we scroll down to our null values in dummy sales, for example, so over here, I know that the real value was 1.48. I purposefully excluded it from dummy sales and then did an interpolation on top of dummy sales using the different methods to see what I would get, right? To see which would be closest to the actual value. All right, let's collapse this. I'm going to add another code block. And in this block, what I want to do is determine the difference between my interpolated value and the real values. To do that, all I've done over here is added for each of my different methods a new column called the method underscore error, so linear error, quad error, and spline error, and then taken the absolute difference, so numpy.absolute difference between the interpolated value and the true value over here, and just repeated that for each of my different methods. Let's run this and see the results we get. So scrolling to the side, we can see that when we do an interpolation on top of dummy sales, we now get a result for the absolute error between the two, or the absolute difference between the interpolated value and the true value. So this gives us an estimate of the error we're introducing. Now, the thing is, mixed in with this, we have a whole bunch of zeros over here, and this is where we have done no interpolation whatsoever. This is actually just the true data, where we haven't actually done the interpolation. So to exclude these, I'm going to add a filter to the data to make things a bit more clear to actually see our errors. Now, the filter I need to add is going to exclude the actual missing values from sales and exclude the values for which I didn't dumbify or didn't purposefully exclude the sales values. So let's make that a little more practical and specify, firstly, I want to filter for errorsdf sales dot is NA, so where the sales are null, but actually I'm interested in where the sales are not null. So to specify a not, I just use the tilde over here, and this specifies not this condition. So let's actually run this and see the result we get. And this is excluded where I have null sales values, so where I have true nulls. Now what I want to do is exclude the values for which dummy sales is null. So to add to our filter, I'm going to specify and with this ampersand character, and specify where errorsdf dummy sales are null. So dot is NA. And this gives me a set of values where I actually have a sales value. So I have a true value where I've purposefully excluded the sales value, and then gives me where I've done my interpolation over here. And we can see we get our different error estimates for each of our different methods. Finally, we would be interested in the average error we introduced, and then the standard deviation of those errors. To compute the average error, I'm going to take our filtered value over here. Let's take that. Let's assign this to a new a new data frame called actual errors df is equal to this filtered values. Let's make it a copy just as a good practice, and then take actual errors and select our different error columns. So that would be, let's say, linear error, quad error for quadratic, and our spline error as well. And then to round things out, let's get the mean value of each of those, or the average value of our errors. We can see that the result over here is for the linear interpolation function, we have an average error of about 4.78. If we were working in dollars, that would be $4.78. The quadratic misses the mark by about $3. And then the spline error is about $2.75. So we can see that on average, spline performs the best. But let's take a look at the standard deviation of our errors to see how spread about those are as well. So similarly, we can specify actual errors df, take our columns over here, our error columns of interest, and use the STD for standard deviation. Yeah, all right, getting these results, we can see that the linear error has a standard deviation of about $6.5. The quadratic interpolation has a standard deviation of about $2.11 or $2.11, and the spline has a standard deviation of about $2. So not only is spline the most accurate on average, it is also the most precise. The errors are fixed around this mean value over here and less spread about, so it is more predictable. So this just justifies that heuristic or that rule of thumb that I mentioned earlier, that typically if you have no other information available to you and you want to use interpolation, a cubic spline is usually the way to go. Now that we've used these different techniques of interpolation, you may be asking yourself, why not just use regression, right, on top of the data? Well, regression is best suited to predicting future values or extrapolating the data, whereas what we were doing was interpolating missing values in between known values. A regression's objective is really to minimize the error between the curve and the data, considering the full data set, whereas interpolation directly uses the data points available to it to fill in the gaps. To give a broad rule of thumb, regression is amazing for predicting future values and analyzing trends, whereas interpolation is more of a cleaning technique than an analysis technique. It's what you would do prior to doing things like regression or using more complex machine learning models. All right, so we've gone through using different interpolation techniques, including linear, quadratic, polynomial more generally, and spline interpolation to impute or infer missing data. And we discussed the difference between interpolation and regression pretty briefly, but discussed it nonetheless. If you have any questions or comments on this topic, let me know in the comments. I'd love to hear from you. And if you found this video useful, please do give it a like and consider subscribing for more insights into data engineering, data analysis, and data science. Now that you have some advanced techniques to clean your data, how do you go about analyzing and answering questions about your data in Pandas? Check out my video on data analysis using Pandas to learn more. Thanks so much for watching, and I'll see you soon.